everyone, we're going to talk today about sigma-algebras and algebras of sets. Okay, so before we step into any proofs, we're going to go over the definition of an algebra and the definition of a sigma-algebra. So this is the definition of an algebra of sets. So an algebra is closed under complementation and under finite union. So if we have a set omega and we have a non-empty collection of subsets of omega, if for every element in that non-empty collection of subsets of omega, if its complement is in the collection, and if it's the union of any two of its elements is in the collection, then we have an algebra. So the definition of a sigma-algebra of sets is really similar to the definition of an algebra of sets. The only real difference here is that for a sigma-algebra, it's closed not only under complementation, just like an algebra, but it's also closed under countably-infinite union. So for an algebra of sets, it's closed under finite union. For a sigma-algebra, it's closed under countably-infinite unions. So we can see here the definition of a sigma-algebra. Of course, the implication here is that a sigma-algebra is an algebra. So every sigma-algebra is an algebra, but not every algebra is a sigma-algebra. We'll look at some examples, some counterexamples to show that there are algebras that are not sigma-algebras. Okay, so here we have a counterexample. So let D be the set of all of the subsets of R such that either the subset A is itself finite or its complement is finite. So it's fairly trivial to see that D is an algebra. I'm not going to show the full proof here. But while we can see that if we have, for example, a sequence of subsets of R, we'll call AN, which consists only of the element N. Obviously, if we take a finite number of these and we take the finite union of them, we'll have that their finite union is itself finite. But what if we take a countably infinite union of these elements? We'll see that if we have a countably infinite union of these elements AN and R, from 1 to infinity, we have the natural numbers. So the natural numbers obviously are not finite, and neither are the complement of the natural numbers in R. So we see here that D is not a sigma-algebra, even though D is an algebra. Okay, so I don't know about you, but I love visual math, so we're going to look at a visual proof. A proof to show that if we have a collection of subsets of omega that's closed under complementation and intersection, then it's also going to be closed under finite union. Okay, so let's take a look at our visual proof. So we're going to start by taking two elements in A-naught, call them A and B. So we take two elements from A-naught. Those are shaded here. This whole rectangle is omega. And we can see that these shaded elements are in A-naught. We've supposed that it's closed under complementation, so that's going to mean that the complement of B is also going to be an element of A-naught. So everything here shaded in red in omega is also an element in our algebra. And also the complement of A is also an element in A-naught. So we also suppose that it's closed under finite intersection. So that means that the intersection of the complement of A and the complement of B is also going to be an element of A-naught. So everything here in red in omega. And then that leads to our conclusion. So the intersection of the complement of A and the complement of B, we take its complement, again, because it's closed under complementation, so we can do that. And now we say that that's going to be an element of A-naught. And we can see that the complement of the intersection of the complement of A and the complement of B is actually equal to the union of A and B. So we just proved that A union B is an element of A-naught. And we can say that for any two sets, any finite number of sets in A-naught, its union is also going to be an A-naught, which means that it's closed under complementation and it's closed under finite union, which means it's an algebra. Okay, so now we're going to look at another visual proof. This time we're going to look at a proof to show that if we have a sigma-algebra, it's going to be closed under countably-infinite intersection. So we're going to start by supposing that A is a sigma-algebra. Obviously, I cannot draw countably-infinite numbers of circles, so we're looking at finite numbers of circles, but you can extrapolate in your mind. So let's take a elements in A in our sigma algebra. So each of these elements is itself an element of the sigma algebra. This whole rectangle here represents omega. So because a sigma algebra is closed under complementation, that means that the complement of A1 is going to be an element in our sigma algebra. Everything here in red is an element of our sigma algebra. Obviously, the complement of A2 is also an element of our sigma algebra in A. So, sigma algebra is not just closed under complementation, it's also closed under countably infinite unions. So now we're going to take the countably infinite unions of the complement of the sequences, the elements of the sequence in our sigma algebra. And that also is going to be an element of our sigma algebra. So everything here in red, this piece here in the center, if you can see, this is not shaded. So this is the only part here that is not a part of that. So what does that all mean? Well, remember that it's closed under complementation, so we're going to take the complement one more time. So we take the complement of this whole thing, and we get just the center here. So we have the complement of the countably infinite complements of the elements of the sequence in the sigma algebra, and that is an element of our sigma algebra. And if we invoke De Morgan's law here, we can see that the countably infinite intersections of elements in the sequence in our sigma algebra is going to itself be an element of the sigma algebra. So we've shown here that for any sigma algebra, it's going to be closed under countably infinite intersection.